So for those of you who don't know me, I'm Christoffer Dall. I'm the tech lead for virtualization at Linaro. Today I'm going to talk about nested virtualization. So I'll cover a little bit of theory about nested virtualization, but mostly I'll assume some existing OS and virtualization knowledge. We have a lot of stuff to go through, and it's a complicated topic, but feel free to stop me if something is completely unclear at some time. So nested virtualization is sort of intuitively the discipline of running multiple levels of virtualization on a single hardware platform. And it looks something like that. So when you run a hypervisor, you run it directly on the hardware, and that runs VMs, right? With nested virtualization, you nest, so you run another layer of VMs inside your VM. We do that by running another layer of hypervisors in between the virtual hardware abstraction created by the first level hypervisor and the kernels running inside your nested VMs. So already at this point it gets confusing to talk about which VMs we're talking about, which hypervisors and so on. So that's a good time to start talking about terminology, which is kind of important when discussing nesting because otherwise people just lose track. So what we do is we call the first level hypervisor that we usually talk about when we run VMs for the host hypervisor. And the VMs that run on top of the host hypervisor, we call those simply VMs, right? Regardless of whether they run just normal VM code or if they also run an additional level of hypervisors and VMs. And the VMs inside VMs, we call those nested VMs. Some people also like to call these things for the L0 hypervisor and then the L1 VM or L1 hypervisor and then L2 VM and so on. That gets handy when you start running even more levels of virtualization. It's confusing on ARM though because we have EL0 and EL1 and EL2 and so on, right? And these things are loosely related. They're not completely separate, but they're very loosely related. So it's confusing and you have to live with it. So why do you want to run use nested virtualization? There's a couple of sort of regular use cases. The first one is if you're an infrastructure as a service provider and you say, we want to provide infrastructure for your existing IT infrastructure in a company that already uses virtualization, well then nested virtualization lets you do that, right? Lets you take a private cloud, move it onto a public cloud, and run multiple levels. People actually do that. Testing and debugging is an important case. Now you want to test a full software stack in a VM that includes a VM. And I think the last one is probably my favorite. It lets people who want to play with hypervisor development using cheap VPS instances, right? So if you have a $3 a month VPS instance and you want to write a hypervisor, you can actually do that. So if we go back to 1974, that's the time when people started talking about nested virtualization the first time, when virtualization as a theory was sort of established in the academic community. Right, so Popek and Goldberg, they said in their famous paper with their second theorem that if you can construct a hypervisor, a VMM, without any strange timing dependencies on a virtualizable machine, then you can also create additional levels of hypervisors. Then the machine is also recursively virtualizable. It's a somewhat trivial proof. So this concept of recursively virtualizable in the theory, that only really applies to sort of classically virtualizable architectures where you can deprivilege your entire VM and use trap and emulate. That's not the case on neither ARM nor x86, right? Here we have these architectures are not virtualizable and we have to rely on hardware support for virtualization. And so as it turns out, when you do nested virtualization on non-virtualizable architectures, it becomes a discipline of figuring out how to do that using the underlying hardware support for virtualization. So let's look at the ARM VE for a minute. That works by expanding the existing protection system where you have EL0 and EL1 for user and kernel mode. With a new mode, EL2, or hype mode. And the idea is that you run the hypervisor in EL2, and you run VMs on top. And then you run your existing user space and kernels in the modes they were designed to do, and you use EL2 to control what these software components can and cannot do. So the central part of doing nested virtualization on ARM is to provide a virtual EL2 instance to run your guest hypervisor. Right? So where before we would emulate a VM that had EL0 and EL1, we're now moving to a world where we have to emulate a VM that has virtual EL2 in addition to EL0 and EL1. And this is basically what the entire work and talk is about. the question is, which physical CPU mode do you run that in, right? Well, there's a couple of options. You cannot run it in EL2, because that's where your host hypervisor runs. So if you run it in EL2, the whole VM becomes as privileged as your host hypervisor, and the whole point of virtualization is lost. So it's EL0 or EL1. With EL0, that's actually possible on today's hardware, right? But it's really slow, and it's really hard to write a hypervisor that does that. But you can do it, and you can trap and emulate like back in the good old days. EL1 is a much better alternative. It's a much faster way of doing it, and it's much easier in terms of writing the hypervisor. It doesn't work, unfortunately, because you can't trap a lot of EL2 operations from EL1 into EL2. So if you, for example, want to read an EL2 system register in EL1, instead of trapping to EL2, it'll undef at EL1. Right? So instead of trapping and emulating, you're getting and emulate. So luckily, ARM fixed this in ARM v8.3. What they do is they introduce a new bit in the hypervisor configuration register, the NV bit. And when you set that, all those EL2 operations that didn't trap before, they begin to trap. You also trap ERET from when you execute it in EL1, so you can emulate it in your host hypervisor. And if you try to read your current exception level when you're in EL1 and this bit is set, it'll lie to you and tell you that you're actually in EL2. So using the ARM v8.3 support, we have a patch set out to support nested virtualization on KVM ARM using that. And as usual, I'll go through sort of the 4 steps of core virtualization: CPU, memory, timer, and interrupts, and see how we use the new hardware features. So the first step in providing nested CPU virtualization is to add the state into memory to represent a virtual CPU that now has EL2 in addition to EL0 and EL1, right? So that's great. It's pretty much a set of system registers. It's an array that you add into the context in your memory. So fantastic, you can then describe a virtual CPU that has virtual EL2, but if you can't really run it, it's not of much help. So small step back. If we consider how KVM works using VHE as an example, what we do is we switch back and forth between your hypervisor and host system to your VM. And when we do that, we, assuming you enter the EL1 kernel in the VM, what you do is when you enter the VM here, you restore all of the EL1 system registers on that virtual CPU array in memory onto the physical EL1 registers on the CPU. Right? When we go the other way, we save the status of the CPU and put that into the array in memory. Pretty simple. When we do this with nested virtualization, you can enter the physical EL1 mode, but you can enter either as the guest hypervisor or as the kernel inside the VM. Right? It's basically the same idea, but the problem is if you enter the guest hypervisor, you want to somehow save and restore these EL2 registers instead, but you're still running in EL1. So a lot of the challenge in supporting CPU virtualization, CPU nested virtualization on ARM, is to figure out a mapping between the virtual EL2 registers you have in memory and the EL1 physical registers that you're going to actually use on the CPU when you run your virtual EL2 and your guest hypervisor in EL1. So this mapping it depends a little bit on the registers, how you do that exactly. So if you consider something like the page table base register, it's pretty easy. They have exactly the same semantics. So you can just take the content of the EL2 register and put it into the EL1 register when you run, and things will just work. The SCTLR is a little bit different. They are similar in what they do. They have similar semantics, but they're different in their bit position. Some things are reserved in one mode and not in another mode. So you have to actually apply logic to translate the meaning of the EL2 register into an EL1 register. The way we do it slightly more mechanically is we come with this concept of shadow EL1 registers. So that's an array of EL1 registers that represent the transformed EL2 registers so that you can emulate your virtual EL2 in EL1. The way we do it in practice is we introduce this hardware pointer. The reason why we call it a hardware pointer is that it's the pointer to the registers that you're going to use in the hardware. And then when you enter the VM, remember that diagram before when you were saving and restoring state, we look at the virtual CPU state and we say, okay, is that virtual CPU state in EL0 or EL1, in which case we point the hardware pointer to the normal EL1 system registers. But if you're in your virtual CPU is in your virtual EL2, and you're going to run your guest hypervisor, you just point it to the shadow system register array. And then all the complicated logic of actually switching between your VM and your hypervisor remains unmodified, because they just follow that pointer. And then you end up emulating the right mode. You also need a mode to switch between EL1 in the VM and virtual EL2, both running in the same physical CPU mode. So trapping from virtual EL1 to virtual EL2 is done by sort of forwarding exceptions. So I can describe this through an example, right? So consider WFI, holding the processor. You can trap that to EL2, and we want to maintain those semantics when you have a nested VM, so you want to be able to trap that from the EL1 kernel into your virtual EL2. When we run the VM, we always trap WFI into the host hypervisor, right? So what we do now is that whenever you execute WFI in EL1 in the VM, that will always trap, as per the architecture, into your host hypervisor. And then we look at things and we consider what should we do. Should we handle it directly or forward it to the VM? That depends on how your guest hypervisor has configured its virtual hardware. So what you do is you look at the virtual hypervisor configuration register. If your guest hypervisor has set it up to virtually trap WFIs, then you forward the exception, and you do that by simply manipulating the virtual CPU state in memory, and then you run your normal switch code, which will now see, oh, I've entered virtual EL2 because you manipulated your virtual P state, switch the hardware pointer around, run the normal switching code, and you'll enter your exception vector in virtual EL2. The other way around, going from virtual EL2 back to EL1, depends on trapping on ERED, right? So what you generally do if you want to change to a less privileged mode from EL2 is you execute the ERED instruction. With RMV 8.3, this will trap when executed in EL1, and the NV bit is set. And the host hypervisor, again, just emulates that exception return on the memory structures and returns, and it works. So if we move on to memory virtualization. Normal virtual memory works something like this. Most of you are probably familiar with this. So you have a set of memory translations performed by the MMU from virtual addresses to physical addresses. On ARM, we call that the stage 1 translations. When you introduce the concept of a VM, you want to be able to virtualize your physical memory and isolate each VM. And we do that with a second set of translations we call stage 2 translations. And your first states become virtual addresses to intermediate physical addresses, and the stage 2 is intermediate physical address to physical addresses. And the stage 2 is managed by the host hypervisor that uses a separate set of page tables. With nested virtualization, you have the same requirements. You want to isolate your nested VMs between each other and be able to virtualize the VM's view of physical memory. The problem is you only have 2 stages of translation in hardware, but you now need 3 to support your use case. So what we end up doing is we end up using a favorite old technology called shadow page tables. And the idea is that you build these shadow stage 2 page tables by, the shadow stage 2 page tables are the ones that you actually give to the hardware that's used by the MMU. And they're built and constructed by the host hypervisor. And what they do is they combine those 2 stages of translation here and here into one page table. You build them on demand, so you initially start out empty, and whenever you hit a fault, what you do is you walk the guest hypervisor's virtual stage 2 page tables in software to figure out the mapping between the IPA and the guest hypervisor's view of physical memory. And the host hypervisor already has an idea of how to map the first level VM's physical memory to real physical memory, and it combines those 2 pieces of information into each entry that you add in the shadow stage 2 page tables. And then you basically rely on the guest hypervisors having to do TLB invalidations, which will trap to EL2, and then you flush your cache shadow stage 2 page table.
So that's essentially you're doing a virtual TLB.
You can describe it that way, yes.
So there's a host hypervisor that does this page table walk in software to construct this?
Yes, the host hypervisor walks the guest's
Page.
stage 2 page tables. And neither, so you don't have a concept of normal stage 2 page tables anymore. Right? They're sort of become transient. And the guest's stage 2 page tables are never used directly by the hardware. Right? Only the shadow stage 2 page table is used by the hardware.
And you can nest only once?
No, you can nest multiple times. What happens then is that the guest hypervisor starts walking your L2 hypervisor stage 2 page table. It creates a shadow stage 2 page table. And then your host hypervisor will walk the shadow stage 2 page tables of your guest hypervisor and create another layer of shadow stage 2 page tables that's used by the hardware.
How did you nest that? Have you tried that?
We've tried 4 levels. Yes, they did. Don't ask me if they were fast, though. Okay, so moving on to timers. So the ARM architecture provides 2 timers for EL1 and EL0, the virtual and the physical timer. You also get a separate timer for EL2, the EL2 timer or the hype timer. You actually get 2 with VG, but that's a different discussion. So again, right, coming back to our first principle, with nested virtualization, you add the capability to emulate virtual EL2 in your VM, right? So again here, now we have to also provide a virtual EL2 timer to the VM in addition to the normal virtual and physical timers. And what we do is we simply multiplex it on software using the timer that the hypervisor uses. So you present a virtual timer to the VM, a virtual EL2 timer, which will cause traps if the VM tries to program it, or your guest hypervisor tries to program it. And then you simply look at, is the shortest deadline my virtual timer programming, or the timer requirements I have on the host hypervisor, and you program your hardware timer for your hypervisor, for your host hypervisor accordingly, and then you multiplex in software. Interrupt virtualization. So I make a point out of never doing a talk without talking about the gig, which we all love. So the gig is the ARM generic interrupt controller. And very, very, very simplified, the idea is that you get a bunch of devices that have lines into the gig, and then the gig can signal interrupts to the CPU up here. And the CPU can then acknowledge an EOI interrupts. The gig has built-in support for virtualization, which we call the vgig. And what that essentially does, again, very, very simplified, is that it adds an additional line into the CPU to signal virtual interrupts, right? But where before those virtual interrupts, where before the interrupts came from real devices, now we're signaling virtual interrupts, which of course don't come from real devices. Instead, they come from a set of special registers called the list registers, which are programmed by the hypervisor. And the advantage of these features is that you can ACK an EOI interrupt without trapping to the underlying hardware hypervisor. So the thing we want to do with nested is we would like to use those hardware features to deliver interrupts to both your guest hypervisor, that's your first level VM, and to your nested VM, so that both of them can ACK an EOI interrupt without trapping. And we do that by, when we run the guest hypervisor, the first level VM, we let the host hypervisor program the list registers, and we signal those interrupts. When we switch into the nested VM, we let the guest hypervisor program the list registers, and we signal those directly. If at this point you have an interrupt for your guest hypervisor, that will go through the host hypervisor, and it'll simply change back. So you switch between the two all the time. In practice, you don't let the guest hypervisor control the LRs directly. You again have this concept of shadow list registers, because you want to sanitize it, and there are some features on the list registers where you need some level of translation. But the same principle applies, that your shadow list registers are sort of a representation to be used by the hardware of whatever the guest hypervisor wrote. In terms of status, we have an RFC v1 on the KVM ARM list, developed by a colleague of mine from Colombia called Jintak. And right now it's all based on a config option. And if you enable that config option, you as user space have the option to say, when I create virtual CPUs, I want them to support nested virtualization and emulate a virtual EL2. So there's a lot of interesting stuff to do still in that work. One thing that I forgot to mention here is that, but I already commented on the list, is that that patch set is like 50 plus patches, and we need to split them up into some smaller series. Probably a split in CPU, memory, timers, interrupts, like I talked about here, would be a good way to do it. There are some obvious things that need to be fixed, like hard-coded address and interrupt numbers, where we have to define interfaces to user space so that it can select them. We don't have any sort of reverse mappings for shadow states to page tables. So if you want to invalidate portions of your shadow states to page tables, what we do right now is we flush everything. And if you run multiple side-by-side nested VMs, if you run multiple guest hypervisors on top of your first level hypervisor, then when you switch between them, we basically flush everything. So that's really slow, so we can do much better. I'd also like to get rid of this config option so that we at least compile all the code every time we compile the kernel. But there's an interesting discussion of whether this should just be a feature that's announced and can be enabled, or if it's something you specifically have to enable on your command line option so that maybe we can remove some of the complicated logic in the critical path using static keys and that kind of things. So there's basically a lot of interesting stuff to look into. So if anybody is interested in participating and has some ideas of something they'd like to do, feel free to reach out to me or Jintag and say, hey, I'd like to work on this part. We really welcome that kind of help. So at this point, I have 4 minutes left for questions and discussions, and as usual as well, a reminder to please go and review the patches. There are 50-some patches, and there are a lot of work for Mark and I to do.
So we have KVM for the first layer of hypervisor and the KVM for the second. Can we mix like a Zen plus KVM?
So our goal in developing this has been to emulate the architecture correctly, so that the virtual EL2 you get is not a thing made for KVM. It is emulating a virtual EL2 as per the architecture. So theoretically, you should be able to run any hypervisor. The way this was developed was actually without a model for 8.3. The initial prototype, the way it was developed without a model, using paravirtualization on current hardware. So that would be a lot of work for another hypervisor. But I don't see any immediate problems. Of course, we have to test it.
Okay. And second question is, have you considered the PCI device as our IOV, how it works in the guest hypervisor?
No, because the platforms, again, that we've used for this don't have PCI. But the prototype that used paravirtualization used both VirtIO and used VFIO pass-through, but not with PCI, with platform, to the first level VM. But we don't have a virtual IOMMU, so you can't do pass-through again to the next level. But we have done both pass-through and VirtIO, but for the first level, but always VirtIO for the second level.
I think that is very important. We need to look into.
Yes and no. Depends on your use case, I think.
Which hardware would it be possible to actually test this on, given the ARMv 8.3 requirement?
I think you need an 8.3 model at this point. Sorry?
Any fast x86,
Yes.
like 4 years ago.
So the prototype that was actually used for academic work and for measurements and stuff used paravirtualization. It was actually quite a simple, I think, like 5 patches on the host and 5 for Linux. And what they do is they say encode the instructions that would have to trap, which don't trap on versions prior to 8.3, into a hypercall payload, and then do a hypercall instead, and then just replace those with a macro. And so we've thought about whether we should make them available or not, so that people could play with it and develop on current hardware with this. I don't know, right? Because then once if we make them available, then people might start using them and support things, and it was a hack job. So I don't know. If people ask for them, we'll probably give them, but I'm not sure we want to try to push them in any more public manner.
Do you have any chance to test the performance of the nested virtualization?
Yes, we have.
Okay, so how about that? How about the data? So
I have to be a little bit careful in what I can say here, but So first of all, the performance we've tested has been with the paravirtualization approach, because obviously otherwise we don't have hardware that can actually run that. So it may not be correct in terms of how an 8.3 system would actually perform. I mean, nested virtualization generally doesn't perform fantastic, also not on x86. There were cases where ARM was the same. There were cases where ARM was worse. I wouldn't move your super critical performance workloads into your nested VM just now. Let me put it that way. But there are ideas on how to improve that.
Are there security implications for walking through the guest hypervisor provided page tables and other lists?
If there are security concerns of walking the guest page tables specifically, I mean, there's the general security concern that if you add a bunch of more functionality into the whole thing and make it more complicated, you have a larger attack surface. I don't think that particular aspect, unless you have really obvious bugs there, is a major security concern. But then again, I'm not a security guy. So, yeah. Anything else? All right. Well, thank you.